Welcome to Lesson 4.7, Modeling and Solving Problems with Quadratic Functions. Now, some problems can be solved by writing, then graphing a quadratic function. In this section, we will write quadratic functions to model a problem, and then solve the problem by using maximum and minimum points and all other information provided. The kind of problems I'm talking about for this section are, remember when I discussed in Unit 3, business or revenue problems where there's a maximum amount of money that we can make or a minimum amount of money that we want to spend. So when we look at those actual problems, it does give us the shape of a quadratic with either a maximum or a minimum. So we're going to investigate some of those problems and use what we know about quadratic functions to help solve them. So there are some steps that we need to take in order to solve a quadratic word problem. First, we need to identify the variables. And by that I mean we need to let some variable represent something of the function. So we're going to use let statements like let x equal or let y equal and so on. Number 2, identify the quantity to be maximized or minimized and write an algebraic expression for this quantity. So we need to define whether it's a max or a minimum problem and what the algebra behind it looks like. So it could be an area problem, it could be a revenue problem, it could be maximum height, something like of that sort. The expression must contain only one variable. If it contains more, use other information and write it in terms of one variable. So we might have to use a bit of substitution and simplifying to have our expression in only one variable. 4. Identify whether the quadratic function has a maximum or minimum value. Then complete the square to determine its value and where it occurs. So from there, that means we're going to be putting our equations into standard form and determining the max or the min. And lastly, we're going to answer the question in the problem. So we're going to answer whether it's a maximum or a minimum and at what value it is. So let's just dive in and do a couple examples. Example 1. Two numbers have a difference of 18. Does their product have a maximum or minimum value? Determine this value and the two numbers. Alright, so before we actually jump into the other work, let's look at this first sentence here. What does that mean? Two numbers have a difference of 18. So we need two numbers. So we need to do our first step here and have a let statement. We need to let x equal one number and say y equal the other number here. And from there, we know that the two numbers have a difference of 18. That means that one number subtracted by the other equals the value of 18. That covers our first sentence there. Now, does their product have a maximum or minimum value? So this is where our second step comes into play. We want the product, say P, which is the multiplication of x times y, to equal either a max or a min. We're not sure whether or not it's a maximum or minimum value yet. Now our third step is to have it in one variable. So we want to take our two equations here and write it in terms of one of the variables here. So say we rewrote this one so that x equals y plus 18 in this case. We could take that and now we could substitute it into our other equation of p equals xy, so that way we have it in terms of one variable. Then we would get p equals xy, which now equals y plus 18y equaling y squared plus 18y. And that now is a quadratic function. From here, we can determine whether it's a maximum or minimum. You see how the leading coefficient here is a positive value? That means that we're going to be opening upwards like so. So we're going to have a minimum value and not a max in this case. Well, what is that going to be, and what are the two numbers that we're going to have? So step 4 says we need to complete the square and write it in standard form. So now we have p equals y squared plus 18y plus completing the square, we get 81 and minus 81. And then we can separate the two and we'll get y squared plus 18y plus 81 minus 81 now. And then this is now a perfect square binomial of y plus 9 all squared minus 81. And hence we have our equation in standard form. Now from our equation in standard form, we can determine that the vertex is going to be -9 and -81. And hence from our y value, we know that our minimum is now -81. And we can also determine what our x and y values were for our original numbers. Well, since we have our y variable here, that means that the y value we had was going to be -9. And from there we can find our x value by subbing back into that equation we had. -9 plus 18, which also equals -9. Hence, we have a minimum value of -81. Hence, our two numbers that multiply together to have our minimum of -81 are -9 and +9. Awesome. There is one example of a problem that we solve using quadratic functions. Now let's try another one. Here we go. Every week, a takeout restaurant sells approximately 2,000 chicken wraps for $1.50 each. Through market research, the restaurant manager determines that for every 10-cent increase in price, she will sell 100 fewer wraps. Part A. What is the price of the wrap that will maximize the revenue? So this is the perfect example of what I'm talking about for the business problems that we occur when we're dealing with revenue. So in order to solve this, we need to know what revenue really is. Well, revenue is the number of items that a business sells multiplied by the price per item. The amount of money that they're going to make due to their sales. So what do we have in our problem in this case? We have that 2,000 chicken wraps for $1.50 each, and we say that 10-cent increase in price, 100 fewer wraps. So we're going to use that to help our equation here. But first of all, we need to identify our variables. So let's let x here be the number of increases in price, because we're testing to see what the max revenue will be. Due to our revenue equation here, we have that 2,000 chicken wraps will decrease by 100 wraps for every increase of price, because x is our increase of price. And that is multiplied by the price per item, which is $1.50 each, plus that 10-cent increase for however many increase there are. So now we have an equation that represents the revenue of the number of items sold times the price per item. Well, from here, we can distribute and solve for x. So let's get 3,000 plus 200x minus 150x minus 10x squared. Well, let's rewrite that in our normal form, and we'll get 10x squared plus 50x plus 3,000. So this is an equation in general form. But in order to find the max, we need to put it into standard form. So let's go ahead and complete the square. So we're going to get, this should be a negative. negative 10 onto x squared minus 5x plus 3,000. Completing the square, we get negative 10 onto x squared minus 5x plus 6.25 minus 6.25 plus 3,000. And we get negative 10 onto x minus 2.5 squared plus 3,062.50 as our equation now in standard form. Now, once we have it in standard form, we can see that our max revenue is going to be the value of $3,062.50 for 2.5 increases, because our x represents the number of increases. So the question was asking, what is the price of a wrap that will maximize the revenue? Well, our max revenue here is due to 2.5 increases, so that means we need to add 25 cents. Add 25 cents to the price that we already had. Hence, we get $1.50 plus 25 equals $1.75. That is the price of a wrap that will maximize the revenue in this problem. Well, part B is asking what is the maximum revenue. Well, we already found that. We found out that the maximum revenue is $3,062.50 for 2.5 increases, which is $1.75 per wrap. There we go. That is our maximum revenue in this problem. So we're going to be working with problems similar to this, where we need to find either the maximum or minimum using the techniques that we have discussed. Great work, and keep it up.